Everyone, I am Arshiraj.
So, hi, I am Sugam.
Hi, I'm Josiah.
I will be presenting our project on scalable recognition using vocabulary tree. So here in our demo, we will be presenting our database and the input images for which we ran our whole code. So at the starting, we ran our code for 50 images and we used orb feature detector for it, and it had like 243 word counts and the 243 leaf nodes into our vocabulary tree. And using this, we can see that our input test image and the is getting the same image as the best match into our database. After this, we ran our code for 5,000 images in the Coco dataset. So for this Coco dataset, we also used orb, and for this we were using like 3 clusters and having 5 levels into our whole vocabulary tree. And at the end, it was storing the bag of words at the leaf nodes. Yep. As you can see that it took some time for the for the 5,000 data set, but it was relatively faster than other feature detectors which we ran for. The orb was the fastest. Brisk and Akaze took some more time. So here we can see we have like 2 clusters and 5 levels, and which will be having like 32 leaf nodes. We are running for smaller data sets and smaller KNL values for the sake of this demo. And after this, we built the histograms for each images, and then we built the bag of words for all the images. Then we save the database into our file, and then after this the database has been built, and then we will be querying our input image. So this input image is not in the database, and we will be using this image to get the most similar looking image into our 5,000 Coco dataset. So for getting this dataset, we will be running the ransack algorithm to get the inliers for the input dataset. So and this similarity is calculated using the scores given to each of the similar images into our databases compared to our input dataset, input image. So here we can see that our code is running for this input image, and as we can see, we get the best image match into our database with our input image. For the input image, we had a lamp and a laptop. We can see that the yellow colors is quite similar to our best match image into our database. Yes, after this, we also ran our code for videos too, and for the videos, Sugam will explain more about those things.
I'll be talking about the video implementation of our project. So we did the same scalable recognition tree for videos as well. For the first video, we had a London landscapes video, and we ran our vocab tree, trained the vocab tree, and had the query image run on the trained dataset. We tried different feature detectors for this: Orb, Brisk, and Akaze. First one was Orb with 5 clusters and 4 labels. Orb was relatively quicker to build with 49 seconds time to build the database, and the word index count result was at number 225. As you can see, the orb is quite quick, but the reals are not that good for orb feature detector. So we also did Brisk for the same video, for the London landscape video. The Brisk was also implemented using the same way that we implemented orb feature detector, that is with 5 levels and 4 features. Brisk takes a little longer than orb detector, as it's a bit similar to Sift feature detector. So as you can see, the number of clusters here again are 5 with 4 levels. Total nodes are 781. The number of frames detected are 195. The time taken to build a database was 27 seconds for the Brisk feature detector with word index count of 625. That's resulted from number of levels in branching. You can see the reality is a bit better than what we got from the orb feature detector. So we also implemented Sift feature detector for another video called Cessna video, which has the video of a helicopter flying by. We used Sift and it gave the best results as far as all the results were concerned. So Sift took a relatively longer time than all the other feature detectors we used. While building Sift for features, It found the video as cessna.mp4 in our local directory. We did it with 3 clusters and 5 levels. The number of frames detected in the video were 290, with total number of nodes at 364, leaf nodes at 243. The database was built with at time with 152 seconds, and word index count was 243. Then we ran ransack on it to see which amongst all the inliers, the number of images with inliers detected, which of the frames had the best matching possible as per the number of inliers in the video. So here's the video, and we are detecting ransack for our query image on each of the frame detected in this video. You can see the number of inliers are different for each frame that are similar to the query image. So one of them is 13, other is 12. So for the result, if you see here, we have a pretty accurate result, because the start of the video and the end of the video has a different the different alignment of the helicopter in the actual video.
Okay, and what we also wanted to do with our project was be able to have a way to run this over and over without having to like rebuild and do hierarchical k-means every time if we're not putting in new images. And one of the best ways to do this was kind of creating out a new save and load functionality, but that required us to have to make custom serialization functions and deserialization functions for a lot of our custom kinds of mapping and vector nodes that we're creating, especially with this really complicated vocabulary tree. So stack tracing through this just to kind of give you an idea of the private variables that we're storing in our database in general. The bag of words, which is the same size, image of histogram. All descriptors contains all the descriptors matched to their images. If you go number of features per image, it shows for each index of the image that how many features they have, where their index starts on the whole feature list. And then, of course, the vocabulary tree itself, which we had set this one to be K of 5 and L of 5. So that means K, 5 children per each, 5 levels down. So once we get to the actual child root level, then that's where we see the occurrence as an image, and the features relate back to the actual image paths themselves. So as cool as it was to make all this, it was a pain in the butt to try to get into a save load functionality, but it's very important for us to be able to run massive million image datasets and not have to keep building this hierarchical k-means tree every time. And I mean, in the future too, that's really our intention for whoever's using this app, that they don't just have to be sitting and waiting for hours like we did. So this required a lot of customized write functionality and using C++'s built-in file storage module to be able to add in all of our custom components, custom trees, and then we have a file actually which contains all of our data and that we're able to load back in. And so we're able to load all of those pieces, and then at the end, allowing us to skip, what would be just tons of time and processing. The vocab node was definitely the most complicated of the bunch, and we're actually still, our whole hierarchical k-means tree itself is a very complicated, data structure that changes from time to time, even with the same inputs. But it contains all the information correctly. The file node children are being built correctly, so we know that we're at least close to full functionality. And overall, our accuracy has been improving